Math 151, Activity 2.1. This is basically guided notes for section 2.1. So we'll go through this together. There are places where you can fill in the blanks. Oops. Fill in the blanks for definitions. There are some practice problems and examples in here. And we're going to try to get through, well, one, I'm going to try to stop making random lines on the screen. And we're going to try to get through this whole thing. Just in case somebody's watching the video and didn't see, you can find this under the Unit 1 module for the 2.1 information. So 151 OER Activity 2.1. All right, so we start off by defining a function. What is a function? A function is a relationship between two variables, the input and output, such that each input value has exactly one output value. So it's a relationship between two sets of things, objects, numbers. If you pick an input, it should map to or go to exactly one output, okay? All of the inputs could go to the same output, that's fine, but you can't have the same input going to two different outputs. That's not a function, okay? The output Y, let me make this just a little bit smaller. Sorry, you guys. The output Y is called the dependent variable, and the input X is called the independent variable. We have dependent for Y and independent for X. Why? Because usually you pick the X value, and whatever the X value is that you choose, Y depends on that. So Y depends on X. Y is dependent, X is independent. All right, in the next section, we're gonna look at a couple of relations. So there are two sets with arrows indicating which number in the first set goes to which number in the second set. And remember, the first set is our set of inputs. The second set is our set of outputs. That should be said. Input, output, input, output. And we're asked which of these relations represents a function. If we're using our rule that each input has to go to exactly one output, which relation represents a function? Relation 1 or relation 2? 1 is a relation. Why is 1 a relation? The number 1 maps to only one output, the number 2. The number 2 maps to only one output, the number 4. 3 maps to 6, you know, and so on. So yes, this one is a function. Why is relation 2 not a function? So the problem here is with 2. The input 2 goes to two different outputs. So this is not a function. All right, so that's a visual example of how we can show whether two relations represent functions. Next, we're going to take these relations and represent them in table form. We usually use X to represent the input and Y to represent the outputs. So for relation 1, when the input is 1, the output's 2. When the input's 2, the output's 4. And when the input's 3, the output is 6. And for relation 2, when the input is 1, the output is 2. And then for 2, notice we have two inputs of 2. One has an output of 4, the other one has an output of 6. And when the input is 3, the output is 6 also. All right, so when we're looking at a table, in order to determine whether or not a table represents a function, first you want to see if all of the outputs, all of the inputs are different. If they're all different, then you should be fine. It will represent a function. If you have an input that's shown on your table more than once, like here, and it has two different outputs, then it's not a function. All right, on to our next thing. The output, Y, is a function of the input X. If and only if for each ordered pair, X comma Y, or for each, I'm sorry, reading this incorrectly. Y is a function of X if and only if for each X, there is exactly one Y. So this is just restating the definition of the function. Each input goes to exactly one output. And then we can write this in function notation. Function notation would be y equals f of x, and this is read, y is a function of x, okay? We can plug in numbers for x, and then depending on what the function rule is, we can get out numbers for y. An example of this would be f of 1 equals 2. This means when x is equal to 1, y is equal to 2. Or when the input is 1, we get an output of 2. All right, one page down, just so you guys know where we're going with this. We have like 4 pages on here. 4 pages. So one page down, 2 more pages to go. All right, next we're going to look at graphical and table examples where we're asked to determine whether or not the graphs and tables represent a function. If you are given a graph, you determine if a graph represents a function by using something called the vertical line test. Basically, draw a vertical line through the graph, or draw as many vertical lines through the graphs as you want. Every single vertical line drawn through your graph should only touch the graph in one place if it's a function. If it touches the graph in more than one place, it's not a function. So for example, with graph A, that's an absolute value function. If we draw a vertical line through here, any vertical line, boom, there's one, there's one, there's one, the y-axis is 1. These vertical lines only touch the graph one time. That means that this is a function by the vertical line test. However, with graph B, we have a circle there. I draw any line through this circle, it's going to touch the circle at 2 different parts. This is not a function. Why not? Because for whatever x value we have here, it has 2 different outputs, this y and this y. So we have one input that has 2 different outputs. That doesn't work. By the vertical line test, this is not a function. All right, for parts C, D, and E, I want you guys to try and think about these. So this, tell me if parts C, D, and E represent a function or not. So take a moment to work on these, and then we'll solicit answers shortly. All right. So for part C, does the table in C represent a function? This one represents a function? Yeah. All of the inputs are different, so there's really nothing to check if all of the inputs are different. So yeah, this one's a function. What about D? Oh, if no, why not? Which number gives us a problem? Remember, it's okay for all of the y values to be the same. We just want to make sure that there is no x value that's going to more than one y value. So there can be several different x values going to the same y value. That's fine. You can't have y values going to the same x value, if that makes sense. So actually part D is a function. It's perfectly fine for all of the y values to be the same. Okay. And then for part E, does E represent a function? Yeah, -3, the input of -3 goes to 2 outputs, 6 and 9. So that one is not a function. For G of -3, we're replacing the x in the x squared minus 5 with 3. You want to be -3, I'm sorry. You want to be careful here and make sure you include the negative when you square. So that's parentheses -3 all squared minus 5. This would give us 9 minus 5, which equals 4. And we're not asked to do this, but let's just go ahead and write the ordered pair. So we have the ordered pair -3, 4 on the graph of G. All right. And then next for the square root of 3, that would be the square root of 3 squared minus 5. The square root of 3 squared is 3. And then 3 minus 5 is -2. So we have the ordered pair √3, -2. All right. And then for part B, okay, here our function is -x squared. So you square x and then you negate it. Okay, so your answers are going to be negative here. All right. For m of -5, be careful here. This is negative, parentheses, -5 squared. -5 squared on its own is positive 25, but then we have another negative out front. So the answer here ends up being -25. And we get the ordered pair, -5, comma, -25. All right, then for -√3, we have negative -√3 squared. -√3 times -√3 is still +3. And then we have the negative out front. So this answer would finally come out to be a -3. And we get the ordered pair, -√3, -√3, comma, -3. The next few problems deal with finding the domain and range of a function. The domain represents the set of all possible inputs we can have for a function, and the range would be the set of all possible outputs. So the input will be all of your x values, the output is all of your y values, okay? For some functions like linear functions and polynomials, the domain is all real numbers. You might be familiar with that. And then for other functions like the square root function, we can only take the square root of a positive number. So that restricts our domain and our range. So let's look at these. Using interval notation, determine the domain and range for the following functions. So for f of x equals 3x. So 3 times x. For the domain, you want to ask yourself, what numbers can I multiply by 3? Any number. You can multiply any number by 3. That's actually an example of a linear function. The domain for a linear function would be all real numbers in an interval notation. That's -∞ to -∞. I'm sorry, -∞ to +∞. And what are the possible outputs you can get? If you think about what the graph of a line looks like, it goes on and on forever. So it'll cover every x value as well as every y value. So the range would also be -∞ to infinity. We think about what the graph looks like. Sometimes visualizing these things or going through the graph also helps. This is clearly a very, very, very rough sketch, but 3x will look something like this. The graph goes on forever, so every x value gets covered and every y value gets covered. So the domain and range contains every x value and every y value. All right, for part 2, f of x equals 2x squared. Okay, what numbers can we square and multiply by 2? You can square any number, you can multiply any number by 2. So the domain, again, for this function would be all real numbers, -∞ to infinity. However, the range, if you square a number and multiply it by 2, is it possible to get a negative number as your output? No, it's not possible to get a negative number. So when you square a number, it makes it positive or 0, if you have 0. And then when you multiply by 2, it's just more positive or 0. So for your outputs or for your range, it's not possible to have a negative number. So the range for 2x squared would be from 0 to infinity. Okay? And then I left a 0 blank because 0 is included. If I plug in 0 for x, I get out 0 for y. So 0 is included in the range. We would want to put a bracket around the 0. That means the outputs can be any number from 0 to infinity, including 0. And then the last one's the fun one. F of x equals the square root of 2x. Also, hold on, I feel like I'm not being thorough here. I sketched the other graph, I didn't sketch this one. So for f of x equals 2x squared, that would be an upward opening parabola. It's kind of narrow, or something like this. You can see it's going to cover every x value because it keeps going up and out, but it never goes below the x-axis, so no negative y values. And then for the last one, the square root of 2x, what type of numbers can we take the square root of? For this class, we're only looking at real numbers, no imaginary numbers for now. So we can take the square root of only positive numbers. That means when we plug in a value for x, we have to get a positive number out. A positive number out of 2x. Or another way we can think of this is if we take whatever is under the radical, 2x, that has to be greater than 0. So this means that x has to be greater than 0. That is our domain. So for a square root function, what's under the radical has to be greater than 0. And in this case, that means x has to be greater than 0. Or equal to, technically, or equal to. So we have 0 to infinity for our domain. For the square root of 2x, we can only plug in numbers from 0 to infinity. And then when we take the square root of something, is it possible to get the square root of something being negative? No. So again, our outputs will be the numbers from 0 to infinity as well. So both the domain and range are 0 to infinity for the square root of 2x. All right. Any questions so far? So next, this is a big part of what we do in this class and the way that we present examples. We've talked about functions and we've looked at the function rule using like algebra, right? We have looked at a few graphs. We looked at tables. All of those are different ways that, or verbally, all of those are different ways that we can represent functions. And we talk about things in this class in all 4 ways. So when we talk about a function, you need to know how to represent that function in words, verbally, with a table that's numerically, with a graph that's graphically, or algebraically using symbols. All right, so filling this in. When we say verbally, we mean literally using words, okay? So using words. When we say graphically, we mean we want to be able to represent a function using a graph. When we say numerically, numerically means using a table of values. So using a table. And then when we say algebraically, we mean like using the equation. Sometimes it also says symbolically, so using symbols, mathematical symbols. All right. I've been skipping our little notes on the side, but the notes are important to read as well. They give a little bit more insight into some of the problems. All right, in example 4, let f be a function represented verbally as the output is 1 less than twice the input. So that's an example of written in words. We want to translate that into a mathematical equation that'll be written algebraically. And then once we have that, we can pick values for our input, find the output values, and get a table. And then once we have our table, we can plot the points and find the graph. So let's do all of that together here in example 4. All right, how we can translate the output is 1 less than twice the input into function notation. The output is y, or f of x, equals is, how do we write 1 less than twice the input? So it's 2x, that's twice the input, and then 1 less than that, minus 1. All right, so that's our function rule. Now that we know our function rule, 2x plus 1, I'm sorry, 2x minus 1, we can use that and plug in these x values that were given to make our table, -4, 1, 0, 1, and 5. So we have 2 times -4 minus 1, that's -9. 2 times -1 minus 1, -3. 2 times 0 minus 1, -1. 2 times 1 minus 1, 1. And 2 times 5 minus 1, which would be +9. All right, these give us ordered pairs. -4, -9, -1, -3, 0, -1, 1, 1, and 5, 9. All right, then the last part here. Oh, I'm gonna skip the domain and range at the end. Now, It says, what's the domain and what's the range? The domain would be all of the inputs and the range would be all of the outputs. What we have in the table doesn't represent every possible input or every possible output. We want to go back to the original function. What numbers can we multiply by 2 and subtract 1 from? Any number that's aligned. The domain would be all real numbers, negative infinity to infinity, and the range is also negative infinity to infinity. All right, let's plot these points. The first one, -4, -9, sorry, would be here. The next we have -1, 3. Then next we have 0, -1. Then 1, 1. And finally 5, 9. And then once we connect all of these, we'll have a graph of our line. This just helps me draw a straighter line than I was about to draw. Boom, ta-da, that's our graph. And technically our graph should have arrows at the end to indicate that it keeps going on. So now we've represented this function in words, algebraically, numerically, and graphically. All right, so problem 4, page 4 does have some problems where we look at the domain and range of different functions, lines, absolute value functions, and square root functions. I can go ahead and do this. We already said for something like a function x or 2x plus 1, that's a linear function if the graph is a line. The domain and range are both all real numbers. And we can see that from the picture, the graph continues going up and down in both directions. So eventually every x value and every y value will be covered. All right, for x squared, we look at the graph, that parabola, it is above the x-axis. The ends keep going up, so eventually they're going to stretch out and cover every possible x value. So the domain is all real numbers, but the y values never go below 0. So the range would be from 0 to infinity, including 0. All right. This is the last two. All right, absolute value functions and square root functions. So for this absolute value function, the absolute value of x, when we look at the graph, similarly to what we saw for x squared, the graph is above the x-axis and it's going up on both ends. So it continues to increase. The domain here is going to be all real numbers. We can take the absolute value of any number. But what happens with the absolute value? It takes whatever number you plug in and makes it positive. So our outputs can only be positive numbers or also 0, so non-negative numbers. Bracket 0 to infinity. That's our range, all of the possible outputs. And last one, the square root function. We're only dealing with real numbers right now. So if we take the square root of a number, it has to be a positive number. And then when we get what we get out is also going to be a positive number. And if you look at the graph of the square root function, it's all contained in the first quadrant where both x and y are positive. But also 0, 0 is a point. So it would be from the domain 0 to infinity, including 0. And the range is also 0 to infinity, including 0. All right. And that ends our first packet. Now, I have 8 minutes. I want to make sure we're all ending on the same note and set up properly to be able to be successful